Hello everyone, my name is Mina Ghodsi Yengejeh and I'm a PhD student at Konkoly Observatory. Today I would like to talk about how we created ISW maps for Gower Street simulation. But at the beginning I would like to acknowledge my supervisors and my colleagues who have supported this work. Okay, I will start with two lines, didn't read the slide. So we generated ISW maps for 777 different realization of Gower Street simulation. Gower Street simulation is a full sky n-body simulation based on wCDM cosmology. So it has 7 different cosmological parameters. They are changing. It's based on forward model. So it has realistic observable like photozero, shape nodes, etc. To create these ISW maps, we needed to use pyGenISW and Terrestrial, two publicly available packages. But the problem is that they only support ΛCDM. So we needed to extend and improve these two approaches. And we also added some multiple approaches to calculate, for example, um, growth factor and growth function. So we improved it also in that case. And at the end, I will also talk about our ongoing project, how we are right now we are trying to find. Hello everyone, my name is Mina Ghodsi Yengejeh and I'm a PhD student at Konkoly Observatory. Today I would like to talk about how we generated ISW maps for Gower Street simulation. But at the beginning, I would like to acknowledge my supervisors and my colleagues who have supported this project. Okay, I will start with too long didn't read the slide to have a big picture of the idea. So we generated ISW maps for Gower Street simulation for 777 different realization of Gower Street simulation. Gower Street is a n-body full sky simulation and is based on wCDM. It has 7 different cosmological parameters and they are changing. It's based on forward models, so it has realistic observables like photozeros, shape noise, etc. To create these ISW maps, we wanted to use two publicly available packages, pyGenISW and Terrestrial, but the problem is that these two packages only supported ΛCDM model. So first we needed to extend and improve these two packages. We also added multiple approach to how we can calculate growth factor and growth rate, for example, and how we can also consider massive neutrinos. And at the end, I would also like to talk about our ongoing project that we are using 2D void finder and how we can use Gower Street simulation based on wCDM cosmology to find an answer to cold spot on our CMB. But first, I will start with Gower Street simulation. As I mentioned, it's an n-body simulation. It's a full sky. It provides like in different light cone slices. It has 791 different cosmologies. First, it was built for dark energy surface based on using simulation-based inference. It has 7 different cosmological parameters: omega m, omega p, h, and s, neutrinos, and sigma 8. And they also use forward modeling, so they added more realistic observational effects to this. But why we are interested in Gower Street simulation, the most important thing is that it has a large number of full sky n-body simulation. As a part of this project, we want to use these outputs as an input for machine learning. So we needed to have more and diverse and different kinds of cosmology with different kinds of cosmological based on different cosmological parameters. They use formal model, so it has more realistic observable. It has wide range of different cosmological parameters. So when it comes to explain different effects, we have a wider range to see the dependency of each of these parameters to what we can see. It has a high and good resolution, at least for us, to study ISW, and also very importantly, it's publicly available. But what is the ISW, or what is the late time integrated Sachs-Wolfe effect? Actually, the ISW effect is a secondary CMB anisotropy along the line of sight. So when this photon is coming, for example, from CMB toward us, during the matter-dominated era, gravitational potential stay almost constant on linear scales. But during the accelerated expansion, this gravitational potential evolves with time. So these blue shift and red shift here they can cancel out each other, but here they cannot cancel out each other. So we see some anisotropy. The ISW signal are subdominant to compare with other primary CMB anisotropy, but in larger scale and or small multiples for L below 100 or 200, we can expect to see the effects. As I mentioned, to create these maps, we use two publicly available packages, but we needed to extend and improve it. These two packages are pyGenISW and theoretical. That Krishna Naidu developed them. But how this works, how the whole pipeline works, that we can have one ISW map. First, we need to fix our cosmological parameters. As you can see here, right now it accepts 7 cosmological parameters. You can fix them as the first step, theoretical, or after we modified it, extended version of theoretical, use all of these 7 parameters to calculate some function that later we need in the ISW kernel, like co-moving distance, h of z, growth function, growth rate. So this is the first. But on the other hand, we have in Gower Street, we have dark matter particles in different redshift slices. So first we create density contrast map in each of these slices, and then we give this as an input to extended version of pyGenISW. The first step is in pyGenISW is the harmonic decomposition. This is the angular part. It breaks the sky pattern on each shell into angular wave patterns. So now we know how strong each angular scale is at each redshift. The next step in extended version of pyGenISW is a spherical Bessel transform. This is the radial part. This actually breaks the radial direction into radial wave patterns. Or in another word, we can say that we want to know how matter fluctuation in 3D, how matter fluctuates in 3D. So we decompose radial direction into different radial wave modes. And then it comes to calculate the ISW kernels. Actually, the ISW kernel tells us how much a gravitational potential at a specific redshift of z contribute to the CMB temperature shift. And at the end, we can have a map and output something like this. And here we consider everything from redshift 0 to 1. So we are integrating, we're adding all of them together. We created for 777, but we have 3 representative, and I would like to, because you see these 3 representative everywhere from now on, I would like to talk about our 3 representative. Its simulation 742 has a W equals to exactly -1. We consider this as our ΛCDM model. Simulation 127 has the smallest value for W, which is the most extreme phantom model. And simulation 401 has the largest value for W, that we consider this as a representative of the most extreme quintessence model. And you can see the output ISW maps. Actually, I removed low L below 10 here to see it better. These are the output ISW map. But how we can explain why we have more pronounced signal, we have a stronger signal in simulation 401 or our quintessence model, for example, rather to our ΛCDM or phantom model. To answer to this question, we can look at this plot. Actually, I didn't use all of these cosmological parameters, so I tried to keep it simple. So only three different W, I changed their W parameter. What is important here is that, as I said, the ISW effect, we can see that in when the universe is in the accelerated expansion phase. So here, when each of these curves are passing this horizontal dashed line, they are going to lambda dominated or yes, dark energy phase. And as you can see, the quintessence model entered this phase much earlier, for example, to compare with phantom model, even though in phantom model we have a huge, like very strong uh, expansion, accelerated expansion, but because the integration, the adding all of this together is also important, and because quintessence is lambda dominated much earlier, we can see more a strong signal here. In another word, we can also see them in this histogram. This is this panel shows from redshift 0 to 1, so all of them together. And as you can see, 401 or our quintessence model can shift the temperature more than compare with, for example, 127 or phantom model. So this can shift much stronger than this. But for example, in this slice, in this redshift being from zero point 0.8 to 1, because 127 phantom model, sorry, it's not a still around here. It's not a still. It's deeply in matter dominated. It's not in lambda dominated era. We don't expect to see any shift due to the ISW. But because quintessence model is already in the lambda dominated era, we can expect to see some shift. But in a very low redshift from 0 to zero point 0.2, because three of them, they are already in lambda dominated era, we can expect to have this almost similar shift due to ISW effect. Well, we have ISW maps. We can calculate the ISW auto and cross power spectra. This is CTT and this is CTG. Actually, we don't have galaxy here, so for cross correlation, I use the density contrast map from the same exactly redshift from 0 to 1. In both panels, in top panel, you can see this dashed line, which is coming from theoretical prediction. This is coming from extended theoretical, and solid line is coming from Gower. It's coming from our maps that we generated from Gower Street, and this shadow part is 1 sigma. And in the bottom panel, you can also see the ratio of these auto and cross power spectra compared with theoretical prediction. We also added PyCCL result here to make sure the accuracy of our model, and you can see it has a very good accuracy. And to calculate this central value and error bars, we use all the 777 realization. And this shadow for anything for L below 10, actually our results are not very reliable, but the problem is coming from the box size limit of Gower Street simulation. The box size of Gower Street simulation is 1250 megaparsec over H, and you can easily calculate that for anything below 10 or 11, results are not very reliable. So this is not coming from our packages, but this is only because of the box size limit of simulation. The ongoing the project that right now we are also working on this is right now we have like different slices, this Litecoin in different slices. For some of them are very at the beginning, especially it's very narrow, so we need to merge a few of them to make sure that we have slices with delta z almost equals to 0.05. Then we are running 2D void finder on each of these. But how this 2D void finder works is that first of all we create density contrast map from each of these slices. Then we smooth it a little bit because It's like ISW is a big has big features, and then we sort all the pixels and we start from the smallest value. We select the most underdense region, and then we expand around that with expand the radius around that until we reach to the mean density. And then with that we can extract some information, for example array and deg of that void, radius of that void, and how empty it is, for example, like delta. And then it comes to cut out those parts from our ISW maps. And because ISW signals, they're already, I said, like, they're very, very weak, and they have very low signal to noise. But if we cut out all of them and stack together, we can increase the signal to noise. But why we would like to do this? The main idea is coming from actually this paper in 2020. András Kovács et al. They showed that with ΛCDM model or simulation based on ΛCDM model, we cannot explain the cold spot, or the CMB cold spot. But right now we have 777 different universes. Some of them they have the most extreme cosmological parameters. So we want to see, is there any universe in Gower Street simulation based on wCDM model that can explain our coldest spot or not. So to sum up, we extended and we improved two publicly available packages to be able to handle our wCDM-based cosmology of Gower Street simulation. If you would like, you can send an email to me. I will provide it to you. Right now, we are running 2D Void Finder to see if based on Gower Street simulation we can explain the CMB cold spot or not. Thanks for your attention.